what mathematics does is it allows a person who's been trained in it to understand this process of going from concrete figures to abstract forms, from concrete thought of actual objects to lifting those thoughts out of the concrete and into the abstract, and passing from one to the other. Hello, and welcome to this week's lecture in this series on K-12 education, where we will be looking at mathematics and the place of mathematics within the curriculum. In this lecture, I'd like to spend quite a bit of time discussing the purpose for the study of mathematics, since that will dictate to a large degree how we go about that study. We will look at how the ancients approached the study of mathematics and how and when a shift took place in educational philosophy. Finally, we will discuss current views of math education and what that means in our children's schools, both in the type of mathematics and the depth at which it's understood. I would like to begin with an excerpt from C.S. Lewis's The Screwtape Letters, maybe an odd beginning to a talk on mathematics. The Screwtape Letters consists of a fictional correspondence between demons, the senior demon, Screwtape, writing to his nephew, and junior tempter, Wormwood. It is clear in the book that Screwtape acts as a mentor to the young Wormwood in his job to lead the patient, that is a human, to the father below, Satan, and away from the enemy, God. In the first chapter, Screwtape writes, "But are you not being a trifle naive? It sounds as if you suppose that argument was the way to keep him out of the enemy's clutches. That might have been so if he had lived a few centuries earlier. At that time, the humans still knew pretty well when a thing was proved and when it was not. And when it was proved, they really believed it. They still connected thinking with doing and were prepared to alter their way of life as a result of chains of reasoning. But with the weekly press and other such weapons, we have largely altered that. Your man has been accustomed, ever since he was a boy, to have a dozen incompatible philosophies dancing about inside his head. He doesn't think of doctrines as primarily true or false, but as academic or practical, outworn or contemporary, conventional or ruthless. Jargon, not argument, is your best ally in keeping him from the church." Along with Lewis's criticism of the weekly press, I would like to add changes in educational philosophy, in particular mathematics education, as deserving criticism for the problems that Lewis saw in the argument and reasoning skills of his fellow man. So let us take a look at the place of mathematics in history so we can see what occurred in the last 100 years to lead man to such a sorry state. It was the Greeks that brought reasoning into mathematics. In fact, mathematics, as we understand the term today, is entirely a Greek gift. Prior to the Greeks, Egyptians and Babylonians developed arithmetic and geometry, in which they relied heavily on empirical data based on their experience. There was a heavy emphasis on practicality of mathematics, rarely attempting to answer questions extending beyond what was necessary to operate in daily life. They built up arithmetic and algebra to deal with such issues as money, with simple and compound interest, computing wages and dividing inheritances, and in geometry, computing volumes of granaries and areas of fields. They also created calendars to predict natural occurrences for agricultural and religious ceremony. Their advancements in mathematics primarily relied on empirical data instead of abstract reasoning. It was the Greeks that first lifted mathematics out of this experience and empirical data and began studying mathematical objects in the abstract by relying on the nature and properties of the objects rather than on the objects themselves grounded in the physical world. They were able to push mathematical knowledge beyond what was previously known. Set up in the abstract, reasoning can now take over to form the basis of mathematical thought. One of the greatest gifts given to us by the Greeks was this gift of improved reasoning. And this reasoning was brought into, honed, and perfected in mathematics. Mathematical results became a chain of propositions arising out of preliminary assumptions and advanced by reasoning. I'd like to give an example of the type of abstract reasoning that the Greeks brought into mathematics. The following example was mentioned in chapter 23 of book 1 of Aristotle's Prior Analytics, but it probably dates back a couple centuries earlier to the Pythagorean school. The Pythagorean school was founded by a man named Pythagoras. Not much is known of Pythagoras, but that he was born around 570 BC on the island of Samos, that he may have studied under Thales, and he traveled throughout the East and was likely influenced by Hindi philosophy before returning to the Mediterranean area and founding his school in southern Italy. It is not certain which new knowledge that came out of his school can be directly attributed to Pythagoras, since any new knowledge out of the school was given credit, Pythagoras was given credit for. The Pythagoreans held a philosophy that rested on the assumption that whole numbers ruled the universe. That is, whole numbers are the cause for various qualities, not just quantities, of man and matter. Therefore, they undertook a deep study of whole numbers and their properties to better understand the qualities and therefore themselves. Now, because of this mystical view of whole numbers, the Pythagoreans thought that all numbers should be made up as ratios of whole numbers, what we would call fractions. By being able to lift their thinking to a more abstract level, they were able to show that the square root of 2 could not be written as a ratio of whole numbers. I would like to share this beautiful, fairly short argument, which dates back to about 500, the 5th century BC. The only thing we have to remember in this argument is what it means to be an even number. An even number is divisible by 2. An even number can be written as 2 times some other whole number. So suppose that I can write the square root of 2 as a ratio of whole numbers, p divided by q. Okay. Now, the only other thing that I ask is that p over q, this fraction, be written in reduced form. So I don't want to write my fraction as 2/4. I don't want to write it as 12/15. I would instead rather write it as 1/2 or as 4/5. Okay. So we start with the assumption that the square root of 2 is written as a fraction in its reduced form. Now, the form of this argument is something called reductio ad absurdum, proof by contradiction. We will start with some supposition. We're going to suppose that we can write the square root of 2 as a ratio of whole numbers, and we're going to lead it in argument to a conclusion that says that's ridiculous, that's impossible. Therefore, our supposition will be incorrect. So let's begin just there. Suppose the square root of 2 can be written as p over q, where p and q are in reduced form. Here I mean that I do not want to write my fraction as 2/4, but rather 1/2. I do not want to write my fraction as 7/21, but 1/3. Okay. So if I can write the square root of 2 as p over q, a little algebra will show me that if I multiply each side by itself, then I can write 2 as p squared over q squared. And p squared is equal to 2 times q squared. Well, 2 times q squared is an even number by a definition of what we just said, what it means to be an even number. So that means p squared is an even number. But then we have to ask ourselves, what sort of numbers can we multiply by themselves and end up with an even number? Now, from elementary school, we probably remember that odd times odd is odd, and even times even is even. Therefore, if p squared is even, it must mean that p is also even. Okay. So what we've just found is if I can write the square root of 2 as a ratio of 2 whole numbers, that numerator has to be even. Okay. Now, since the numerator is even, p, we can write that as 2 times some other whole number. Okay. In this case, we'll call it 2 times k. A little algebra will tell us that 2 times q squared is equal to p squared. Substitution would tell us That's the same as 2 times k quantity squared, which is 4k squared. Okay. But all of this can be simplified down to q squared is equal to 2 times k squared. That is, 2 times k squared is now an even number, which means that our q squared is an even number. And if we repeat the argument we just made, we said q squared has to be an even number, which means q itself has to be an even number. So, by writing the square root of 2 as a ratio of two whole numbers in reduced form, we just found out that p must be even, and so must q. But this provides a contradiction. Right? We assume that we started out with a number that was already in reduced form, and if we have two even numbers, we could have reduced it further. Therefore, it means it's impossible to write the number, the square root of 2, as a ratio of two whole numbers. So now that we've just argued that the square root of 2 cannot possibly be written as a ratio of two whole numbers, where do we go from here? We could reject the statement if we do not agree with it and say something along the lines of, well, the square root of 2 probably isn't even a real number. Maybe saying the square root of 2 cannot be written as a ratio of two whole numbers is like saying unicorns cannot be purple. It doesn't matter what we say about unicorns, they don't exist anyway. But then we remember that if I look at a unit square, that is a square whose side length is 1, that the diagonal length of a square is going to be the square root of 2. That is from the Pythagorean theorem, which is known to us and was also known to Pythagoreans at the time. Okay. So saying that the square root of 2 is not a real number is like saying squares don't exist. So we could then reject the result if we used faulty logic or reasoning. I encourage you to go back through this argument and test each step to convince yourself that the reasoning is sound. As sound as it is, though, you have to be careful. I can often convince people that 2 is equal to 1 in what looks like but is not sound reasoning. We can reject the result if the foundation on which we're laying it is shaky. There's quite a bit that we're assuming in this argument. We're assuming arithmetic, and we're assuming a little bit of algebra. But what we're assuming with the algebra and arithmetic are those things that we know about addition, subtraction, multiplication, and division, and all of their properties. So that I can take 1 plus 2 and I get the same as 2 plus 1. Commutative properties, associative properties, distributive properties. If we're confident in our elementary school education, then the foundation on which we're laying an argument like this is exactly that. So after testing all of this, we must accept the result. It was a very difficult step for the Pythagoreans because of their view of the whole numbers in the universe. If folklore is to be believed, the person who discovered and shared this result was taken out into a boat and pushed into the sea because of the loss of centrality of whole numbers by this result undermining the Pythagorean philosophy. What actually happened is not known, but this is often considered one of the first great crises in mathematics because it meant that the notion of number was much more complicated than originally thought. Now, in a half-hour lecture, we can see how a mathematical argument is built up. We do not have time to see how a whole subject, such as arithmetic or geometry, is built up piece by piece, or proposition by proposition. It is this deeper study that gives mathematics much of its strength and beauty. Probably the best illustration of this larger structure of the connectedness of mathematics is Euclid's Element, a set of 13 volumes covering geometry of the plane and space, as well as many results in number theory. Approximately 300 years before Christ, Euclid brought together much of what was known in mathematics up to that point and organized it in such a way that, beginning with a short list of abstract statements assumed to be true, and armed with reasoning, he pieced together a body of knowledge as an extended chain. He did so in such a way that Euclid's Elements became the standard textbook in geometry for the next 2,200 years. The elements have been discarded as required reading for educated people has only occurred in the last 100 years. With the strengthening of the connection between mathematics and reasoning, by Greeks, mathematics would next closely become tied together with philosophy and theology and the natural sciences. I take from Plato's Republic, Book 7, we must endeavor that those who are to be the principal men of our state to go and learn arithmetic, not as amateurs, but they must carry on the study until they see the nature of numbers with the mind only. Arithmetic has a great and elevating effect, compelling the soul to reason about abstract number and rebelling against the introduction of the visible and tangible into the argument. The abstraction that Greeks brought into mathematics should never be discounted in importance. I want to take an extended quote from Morris Klein from his book, Mathematics for the Non-Mathematician. The abstractions of mathematics possessed a special importance for the Greeks. The philosophers pointed out that to pass from a knowledge of the world of matter to the world of ideas, man must train his mind to grasp the ideas. These highest realities blind the person who is not prepared to contemplate them. He is, to use Plato's famous simile, like one who lives continuously in the deep shadows of a cave and is suddenly brought out into the sunlight. The study of mathematics helps make the transition from darkness to light. Mathematics is, in fact, ideally suited to prepare the mind for higher forms of thought, because it, on one hand, pertains to the world of visible things, and on the other hand, it deals with abstract concepts. Hence, through the study of mathematics, man learns to pass from concrete figures to abstract forms. Moreover, the study purifies the mind by drawing it away from the contemplation of the sensible and perishable and leading it to the eternal ideas. One author summed up Plato's position on mathematics in the following way. While a little knowledge of geometry and calculation suffices for practical needs, the higher and more advanced portions tend to lift the mind of man above mundane considerations and enable it to apprehend the final aim of philosophy, the idea of the good. Mathematics, then, is the best preparation for philosophy. With such a strong emphasis placed on a deep and strong foundation and reasoning to advance the subject, how did we get to Lewis's criticism, which he wrote in 1940 in the Screwtape Letters? That might have been so if he had lived a few centuries earlier. At that time, the humans still knew pretty well when a thing was proved and when it was not. And if it was proved, they really believed it. Well, early in the 20th century, the progressive movement began to exert an enormous influence over mathematics education in the United States through education professor William Kilpatrick, who was a protege of John Dewey. One of the results of this influence was the dumbing down of the math education by rejecting the notion that the study of mathematics contributed to mental discipline and subscribing to the idea that mathematics should be taught only to students based on direct practical value. This flies very much in the face of what the Greeks thought of mathematics and is much more in line with the Babylonians and the Egyptians. I offer the following excerpt from A Brief History of American K-12 Mathematics Education in the 20th Century by mathematician David Klein. Reflecting mainstream views of progressive education, Kilpatrick rejected the notion that the study of mathematics contributed to mental discipline. His view was that the subjects should be taught to students based on their direct practical value, or if students independently wanted to learn those subjects. This point of view toward education comported well with the pedagogical methods endorsed by progressive education. Limiting education primarily to utilitarian skills sharply limited academic content, and this helped to justify the slow pace of student-centered discovery learning, the centerpiece of progressivism. Kilpatrick proposed that the study of algebra and geometry in high school be discontinued except as an intellectual luxury. According to Kilpatrick, mathematics is harmful rather than helpful to the kind of thinking necessary for ordinary living. In an address before the student body at the University of Florida, Kilpatrick lectured, "We have in the past taught algebra and geometry to too many, not too few." Over the first half century of the 20th century, algebra enrollment decreased by 57%. Geometry enrollments decreased by 63% over that same period. If you believe Kilpatrick comments are outmoded, I would like to draw your attention to an op-ed piece that appeared in the New York Times 2 years ago. In the article, Is Algebra Necessary?, Andrew Hacker, Professor Emeritus of Political Science at Queens College, City University of New York, writes, "A typical American school day finds some 6 million high school students and 2 million college freshmen struggling with algebra. In both high school and college, too many students are expected to fail. Why do we subject American students to this ordeal? I found myself moving toward the strong view that we shouldn't." He goes on to blame the subject of algebra specifically for many of the ills in public education, including dropout rates. He suggests an alternative course of study, but this course of study cannot really be accessed without a background in algebra. The closing lines of the article state, "It would be far better to reduce, not expand, the mathematics we ask our young people to imbibe." This is an echo of Kilpatrick's comments from nearly 100 years ago, and its sentiment seems to be regaining a more widespread acceptance. After the progressive movement of the early 20th century, many may know the next movement as the New Math movement of the 1960s. And many mistakenly think the New Math movement as a progressive movement. It was actually quite the opposite. The New Math movement was a movement in response to the dumbing down of the math curriculum by the progressives and the Soviets' launching of Sputnik. The counter movement arose to put rigor and reasoning back into the K-12 mathematics. Unfortunately, the new math never grounded itself in concrete mathematics at an early grade. Therefore, the students really never developed a solid foundation, and any reasoning they tried to put on top of it fell to the ground. The students had no firm foundation to build on. Over the last several decades, there have been a back and forth of skirmishes between back to the basic movements and progressive ideas. One of the most influential events of the last 2 decades has been the publishing of the NCTM standards in 1991. NCTM stands for the National Council of Teachers of Mathematics, and it's probably important to note that the NCTM was founded in 1920 to fight against the progressive agenda of the math education community at that time. And now it is one of the biggest proponents of such. These so-called standards see mathematics as a tool for social change rather than a subject worthy of study. Standard algorithms, such as the long division algorithm, are downplayed or completely ignored in the standards. Standard algorithms are standard for a reason. They have stood the test of time as efficient ways to answer large groups of questions. There's something empowering to a student when they know they can answer a question every time. Also in the NCTM standards, deductive reasoning and geometry has been pushed aside as having little practical value. The logic and reasoning that provides the backbone for a math education is increasingly ignored at all levels in the curriculum. If you don't think this spreads across into other areas, I was having lunch with a colleague a few years back, and we were talking about the NCTM standards and how math education in high schools changed. When this faculty member asked me when this took place, I mentioned 1991, but we probably couldn't have seen it in a college until maybe 95 or 96. When this colleague pointed out that in the mid to late 90s, they saw a decrease in the ability of the students to make an argument and to lay out a structure for an essay. Okay. Also, when I'm looking at high school math textbooks and to some degree some of the lower level college textbooks, I always find myself looking at textbooks that were published before 1990 because anything published after 1990 has been influenced by the NCTM standards. Okay. As a response to these more current educational practices, we at the math department at Hillsdale have begun to teach a mathematics and deductive reasoning course. as the core course in mathematics. In that course, we first study logic through both syllogisms and symbolically to understand how it is that we can reach conclusions. Then we apply that logic to the study in depth of Euclid's elements, not for any particular geometric result, but to appreciate order and, yes, beauty in the subject. Now, in much of this lecture, I have focused on what many would consider upper school math. If you are interested in the logical structure of what elementary school math or arithmetic would look like, I would like to direct you to a lecture that I gave 2 years ago in the summer of 2013 for the Barney Charter School Initiative. If you go to the Hillsdale College website and follow it to the Barney Charter School Initiative, you will see a 2013 seminar on a math lesson in which I look at division by fractions from addition through multiplication and division and finally into division by fractions, to not understand just the division by fractions algorithm, but why that algorithm must be the way that it is. Now, in all of this discussion, I do not want to downplay the usefulness and practicality of mathematics. One can find a better job and make more money from studying mathematics. There are ever-increasing uses of mathematics in the sciences and the social sciences. There is a reason the top 3 jobs in most career rankings are mathematically based: mathematicians, statisticians, and actuaries. But we do not study reading and writing to one day read and write office memos and instruction manuals. We read great books as part of a liberal education to understand what it means to be human. In the same way, the same thing is true for mathematics. The ultimate goal is not to achieve the highest test scores for our schools, but to educate our children so that they will have the ability to understand and express great ideas, even mathematically. Thank you.